About 4 years ago, I was head of a testing practice for a European consultancy, and I was going around talking to all the different functions within the consultancy. And after talking to a group of project managers and program managers, one of the project managers came up to me afterwards and asked for some help with an AI project. So, of course, I said, yeah, sure, love to help. What stage are you at? And he said, oh, we're just about to roll it out into the client, who are a major high street bank. Right, what testing have you done? Oh, the devs and the data scientists have done loads of testing on it. Okay, like what? So anyway, I helped them and gave them some ideas, some things they could try, and we tested it and found a whole load of problems with it, so they had to postpone the rollout. They did finally roll it out and it worked and it was okay. But he was lucky because I'd got some background in AI, so I knew where to direct him. And it was at that point that I realized this is common. It's normal in the industry that at that time that the devs and the data scientists did all the developing of AI-based systems, and they didn't think about testing or quality. Who needs to? It's magic, it works. So I started pulling together a toolkit, a basic toolkit that anybody, any of the testers can use. They can pick it up and they can run with it and start testing AI-based systems. Because something else I'd noticed was that most of the conversations that were going on at that time were around how to use AI in testing, as opposed to how to test AI-based systems. So the tools we were using weren't necessarily tested. So how did we know they worked? So how do we test AI? Well, I've got some good news and some bad news. The good news is it looks very similar to the sort of test levels that we're familiar with. And believe it or not, AI has been around for a very long time. There have been non-deterministic systems, fuzzy logic, machine learning, and AI generally for a long time. I did AI as part of my degree 40 years ago. You are allowed to say that I don't look old enough to be. So it has been around for a long time, and certain sectors of defense have been using it for even longer than that. The bad news is we have to change the way we think about it just a little bit, and we have to learn some new skills, and we have to make some friends out there. But I think that's good news, because as far as I'm concerned, I'm a permanently curious learnaholic, so learning new stuff is good. But there are some specific challenges when it comes to AI systems. The Oracle problem is the most well-known one, I think. Basically, these systems are probabilistic. They don't output finite, definite answers. And they're non-deterministic. Run them twice, might get a different answer. So we don't get the nice, easy yes-no answers on the test results. The code does not represent the algorithm. The data does. And that in itself causes some interesting situations. And because the data is what drives it, and because we're essentially trying to do complex things, the data itself is complex and large in volume. And these systems tend to be self-optimizing. They correct depending on what the data is coming through them, which is why they're non-deterministic. System complexity itself, as I say, we're trying to solve complex things. Otherwise, why would we bother? We'd just do them in an easy way. And some of those complex things are trying to mimic human behaviors, and human behaviors by their nature are difficult to define. Bias is quite well known as well. Just about every form of data we have available to us is biased in one way or another. And by being human, we're biased. So, of course, that's going to be an issue. And I think the most famous problem is hallucinations, although a correct term would be confabulations. Because hallucination is where you can sense something that isn't there, or you can't sense something that is there. Whereas confabulation works on the principle of the premise that there is an answer. So you will find an answer, even if there isn't one. And that's more accurately what AI does. It finds an answer, even if there isn't one. And lastly, test coverage. How do we know when we've tested enough? The traditional technique of mapping it back to requirements doesn't really apply. And some of the more traditional coverage mechanisms also aren't really relevant. So these test levels that I said look familiar. So the familiar ones: unit component test, integration testing, end-to-end testing, and UAT. Now this is just a generic test software development lifecycle. These will fit anywhere into the SDLC, wherever makes sense for your particular SDLC, because different industries have different SDLCs. And the newer ones, or new to some people: model testing, data testing, which is familiar to some people, and monitoring live, which some people would argue isn't a test level, but it is still crucial to the quality of the output of the system. So, diving straight in. Warning, I'm going to go fairly quickly through a lot of this stuff, so taking notes is a good idea. If you want a copy of the slides, you're more than welcome to them, and you can always reach out and ask me questions afterwards. So, first one up, component or unit test. Now, generally speaking, this has been done either black box against requirements or white box against the code. Now, since the code does not actually define the algorithm, the data does, and AI has been named as automation without requirements, which is now starting to come into quite a lot of debate. But essentially, if you don't have the requirements to test against, how do you black box test? But, as I say, the data is key here. So every AI-based system has to have a data pipeline in and out of some form. And that's what we need to focus on, the data. So you'll probably recognize some of these techniques, some of these heuristics. Anybody that's ever done any data testing, anybody that's ever done any field validation testing on input forms, on websites or systems that take data in. The false zeros, the blanks and nulls, the outer range values, the formatting errors, the duplications, and if any sort of transformation or normalization is done on the data before it's fed in, then that needs to be checked as well. So this is all familiar. This is stuff that most of us have been doing for most of our careers at some point. And that leads nicely into data testing. So, as I said, if the code is not the algorithm, but the data defines the behavior, then the data needs testing. And we need to be very aware of how that data impacts the behavior of the system. And data is a speciality. So data scientists, data engineers. But we need to be able to inform that. We need to use our critical thinking to help them think in appropriate ways, because they're data scientists, they're not testers, they're not looking for problems in the same way that we do. They're not looking for that risk. So what do we need to be having those conversations with the data scientists about? Bias and fairness. So we need to check the data to ensure that there's no bias within the data, unless, of course, the data needs to match the live environment, because some live environments are biased by their nature. So there's no point using, for instance, face recognition data from an entirely Caucasian population if you're going to use it in sub-Saharan Africa, for instance. You need to use an appropriate data set appropriate to the live. And it needs to be fair. There are systems, tools that you can use for testing this with. AI Fairness 360 is one of them. The other thing you have to be aware of is that there's proxy for bias. For instance, occupation. There are some occupations that are predominantly more one gender than another. For instance, nursery nurse. So that could be biased. Likewise, address. Your address area could be a proxy for race, income, class, and in some areas, age. Where I live, the average age is over 70. So obviously I bring that down a long way. You also have to make sure that the data is suitably diverse and representative. So like I say, it's got to represent the live environment that it's going to be working in. But you also need a full diversity of data, including edge cases. This allows the model to adapt to the real life environment. Labeling and annotation is a very important part of the training process for AIs. And as such, it needs checking to make sure that the granulation of the categorization is suitable, because if it's too broad or too narrow, then you're going to get miscategorization. And it's that probability of which category it falls into that's important in the output. And data splitting problems. Usually what happens is you have a massive amount of data, and some of it's used for training and some of it's used for testing. Roughly 80% training, 20% testing. But if you've split it such that the testing data isn't representative of the environment, or the training data isn't representative of the environment, or the two aren't suitably matched to each other, you're going to get problems. And the way you go about this is statistical analysis. There's some quite easy ways of doing this, as I'll mention later. Some of them are more complicated, and sometimes the interpretation can be quite complex. So you need to cozy up to data scientists. You need to make friends with them. Get them to do the legwork. We don't need to be data scientists, we just need to understand what they're doing. And that's one of the new skill sets you need to think about, is data science. Not necessarily doing it yourself, but being friendly enough with the data scientists that you can ask them sensible questions and get them thinking the way they need to. Next up, integration test. A familiar one again, but these systems are probabilistic, which means they output a probability of it being in a specific category. For instance, the probability of it being a cat, a dog, or a blueberry muffin. Now the problem with this is if you then chain those systems together, as tends to be a necessity because AIs tend to be focused on a specific task and they're good at specific tasks. You need serial AIs, serial models on specific tasks to perform the end task. Well, if you do that, the probabilities multiply, which mean the error factors multiply. So it can get further and further away from the right answer the further down the chain it gets. Case in point is face recognition. First off, you have to recognize it's a face. And as you can see from the blueberry muffins and chihuahuas, that's not always that easy. And then that gets chained into recognizing whose face it is. So remember those error factors. Then we have model testing. Model testing is a relatively new one, but it tends to be the one that people think of as being testing AI systems. And it's essentially testing the performance and behavior of the model in isolation from the rest of the IT around it. And the way to do this is with large volumes of data and doing statistical analysis again. And therefore, we need to cozy up to our data scientists again and get friendly with them. And those large volumes of data can be quite complex to interpret the outputs. So like I say, we don't need to do that. We can get specialists to do it for us. Get the data scientists too. Because they are our friends. There's one thing to remember from this is data scientists are our friends. But they still benefit from our critical thinking, our curiosity, our systems thinking, and that constant question asking that we're well known for. There are tools to help with such things, TensorFlow being one of them. There's lots of libraries in SciPy and PyTorch, for instance, all of which can be used. But you can also do it quite simply using things like Power BI or some of the data analysis modules in PyTorch, quite easy to use, or just using a spreadsheet. Now this, can you see that clearly? It's a bit vague, isn't it? It's basically the distribution data from a synthetic data generation tool that we use at 2i. And this is quite early on in the development. This was a couple of years ago this was taken. And it's basically the real life data compared to the synthetic data to see what the difference is. And I don't know if you can see there, but you can quite clearly see here there's an outlier in the synthetic data. Where on earth's that come from? And there's some there as well that just don't match, they don't line up. So that's a really easy way of doing it. Again, you can see quite clearly on these, there's bits that don't match. And again, we've got this outlier. So that's instantly a hint. We need to dig into that. We need to find out what's going on. And again, you can see the differences here, standing out quite clearly. Another phase, end-to-end. Again, very familiar. But again, beware of that complexity, because the end-to-end, the chances are it's going to have a chain in there and it's going to have a data pipeline in there. So you have to beware of those. And if you're trying to emulate the behavior of an expert, then get an expert to help. Because at this level, we're at system thinking level. You've got to understand it as a system. and the system behavior. It really helps if you've got someone that understands that intimately. And then on to user acceptance testing that we all know and love. Pretty much the same, but watch out for automation bias. Automation bias is the propensity of humans to prefer the decisions coming from an automated decision system over and above those from a human, even when the human is right and the decision system's wrong. It's a classic case of human says no. It's a really weird one. Why would we do that? Why would we trust machines rather than humans? But we do. And at the same time, we expect machines to be more accurate and be 100% all the time, whereas we don't expect that from humans. Weird. And last up, monitoring in live. So although, as I say, this isn't generally considered a testing phase, it is part of quality engineering. And it's absolutely vital to maintain the quality of the output from the system. And when we're talking about performance, we're not necessarily talking about just speed, how fast it is. We're actually more interested in the accuracy and precision in terms of performance. If you consider a cancer detection system, if the accuracy of that starts to change whilst it's in use, becomes less accurate, that can have serious consequences for the people involved. That's far more important. And that change in performance, change in behavior over time whilst in live is called drift. And there's essentially two sorts of drift: the context, concept, or model drift, and data drift. Now, concept drift or context drift is where the task that the model was designed for has changed. So a case in point would be, for instance, scam detection software for an email system. It's based on a certain way that the scammers write their emails. The scammers learn and change their approach to the emails. Therefore, the accuracy drops. So the system needs retraining to bring it back in line. That is context drift. Data drift is where the data input itself changes over time and changes the behavior. A case for this was High Street Bank that was using an AI system for making decisions on loans. And then the COVID pandemic struck. So the data that was coming in was changing. That financial data was changing. And they had to basically retrain all the data for their AI system to get it back to an accurate state. And there's all the other usual testing stuff that you have to consider, all the non-functional, plus accessibility. Accessibility of how the system front end works. Is it understandable? Is it usable? And security. Security is an interesting one. Because the algorithm and the behavior is driven by the data, it means that a malevolent actor could manipulate the data to change the behavior. Now, this is called poisoning the well. So what we can do is what we call adversarial testing. where we do that deliberately and find out how it behaves. There's also some interesting work being done around backdoors in models. So beware the provenance of the model that you're using, because some of the models on public availability have backdoors built into them. And that's a whole other talk. That's absolutely fascinating what you can do with that. And lastly, performance. But as I say, remember, it's not just how fast it can go. It's also the accuracy, the precision, and a whole load of metrics that are available for it. So, quick rundown on test techniques. Explainability. Every single decision-making system has to be explainable. This is all prior to AI and now applies to AI as well. And it's built into the EU AI Act. They have to be able to explain why it came to the conclusion it came to from the parameters it was given. For instance, in a loan decision system. And that's a legal requirement. There are tools that can be embedded into the systems to do that, but it's also useful as a debugging approach. Whoops, sorry. A/B testing, that's probably one that most of us have encountered. Essentially, you put two systems up doing the same thing, compare them, choose which one you like. Parallel testing is an approach to the Oracle problem, in that you basically compare the new system with the original system and run them side by side and make sure that they track each other. There are problems with that, and if anybody wants to hear an interesting story about a financial system, then I'm always open for a beer afterwards. Statistical analysis, that's, as I mentioned, you can do that Power BI, using the tools, using some of the big data analysis tools, or you can just use a spreadsheet if you know what you're doing. Exploratory testing, I'm not going to dig into that one because I'm sure all of you know about it, but AI is a fertile arena for exploratory testing, because let's face it, doing scripted tests doesn't make sense for most AI systems, and especially for Gen AI, for LLMs. It makes more sense to have a charter and run through your charter and explore every possible avenue. Use experts where you can. Use real oracles, real people. And lastly, pairwise or orthogonal testing. This is a mathematical approach that can reduce the number of permutations on inputs. There are free tools available, for instance, pairwise, all pairs, hexawise, that will do those calculations for you, and they can reduce something in the region of a quarter of a million permutations down to roughly 25 permutations. Quick run through the last ones. Metamorphic testing, that's where you put in a perturbation to the input data and see what shape the output comes out as. That's another way of dodging the Oracle problem, because you're not interested in the values that are coming out, only the shape of it. Is it moving in the way that you expect? Adversarial testing, I mentioned that one. Play with the data, see if you can break it, see if you can poison its well. Model back testing is where you take known previous data and outputs, feed it through the new system and compare them. Dual coding algorithm ensemble is basically just take a whole load of them, a whole load of models and then compare the outputs from each. They should all be similar. Choose which one you like the best. Coverage data is where you have a set of data that's designed to trigger all the neurons or nodes within the network. It's not very valuable, that one. It's a bit like code coverage. Not quite sure what it gives you. It certainly doesn't prove the algorithm. It certainly doesn't prove the outputs. Cross-validation, k-fold cross-validation is the most popular one. Basically, you take your data, you chop it up into lots of little segments, you train with all the segments bar one, which you test with, save the outputs, clear it down, do it all again, but using a different test segment. And you do that until you've used all the segments as test segments and compare all of the outputs, and they should be all the same. Affordance modeling is a thing from old design techniques, which is basically if you have a mug with a handle on it, the handle indicates how you should use that mug. So theoretically, a UI, you should be able to understand how to use it by the nature of the UI. And that should feed into your use cases for UAT. And lastly, every AI system, with some notable exceptions that are very hyped at the moment, should be providing something to a human. The human should be interacting with the output from that at some point. It's for a human benefit in one way or another. So the human experience has to be taken into account. Tariq King's talked a lot about this. Really interesting guy, well worth following. He's got loads of experience on AI. Shed loads more than most people I know. Well worth talking to and well worth following. So always consider the human experience in every system. And lastly, hopefully you can see where these tools might fit. Now I'm going to give you a definition of the Holy Trinity that's my definition. We can argue about this externally, but for this purpose, essentially quality engineering is building in quality throughout the whole of the life cycle. Testing is making sure you've built in that quality, and quality assurance is making sure you have the mechanisms and measures and metrics in place to be able to build in quality. So these tools, hopefully, you've seen where they can fit within the quality engineering life cycle, all the way back up to the initial design, the initial, this is what I want, this is the spec. And from that, you can see how that will then fit into quality assurance. How do we assure that we're doing the right thing with the AI system? Now, this is what we've developed at 2i, and we've used it with several clients. Basically, 4 factors: accuracy, robustness, explainability, and performance. And you should be able to see, I don't know if you can actually see it on the screen, but those tools appear in each of these columns. Data integrity, model validation, continuous model monitoring, feedback loops, adversarial testing, transparency, they're all in there. And you can measure those and get a score. And you can tell whether your AI system has a solid foundation of quality to be built on. This slide's a bit out of date, but it's got a few useful resources on it. If anybody wants it, give me a shout. You can have the slide pack. I'll just let everybody take a photo. You don't need to take a photo, you can always ask me at work. Okay, so thank you very much. I know that was a high-speed gallop through it. So as I say, you can always talk to me. You can contact me on LinkedIn. I also host a podcast for the Scottish testing group called Quality Blether. Check it out, it's on all the usual sources of podcasts. Reach out, say hello, connect with me, and if you've got any questions, if you want the slides, give me a shout. Thank you.